Okay, hello everyone. This is section 8, groups of permutations. All right. So we're going to look at another important properties in this section. The first one is we're going to look at how we can say that any groups that we have had looked at so far will be isomorphic to a group of permutations. Okay, this it is quite and it is a very important properties. Okay, how we can say that any group that we have had so far, be it abelian, non-abelian, cyclic or not cyclic, we can say that these groups will or actually isomorphic to a groups of permutation, right? So before we go into that important property, we're going to look at the concept or the notion of homomorphism and kernel, because we're going to use these two important notions into proving that every group is isomorphic to a group of permutation by means of Cayley theorem. And then in the final section of this on the final part of this section, we're going to use the concept of homomorphism into proving that a set of even permutations will form a group. Okay, so we recall what we have had so far from the beginning. When we want to show that a group is a group, we have some axioms by right or by fundamental of a group, but in some cases we have seen in section 3 is also we have shown that some groups is a group just by showing that it is isomorphic to another group. That was what we did with integer modulo n, right? So integer modulo n, we show that that integer modulo n is a group by isomorphism with n truth of unity. So we show that n truth of unity is a group first by using the group axioms. All right. So that is also what we're going to look at in this section at the end of this at the final part of the section, where we will see that a set of even permutation will form a group by using this homomorphism property. All right. So pay attention to these two notion, because we're going to use this homomorphism and kernel in the later part of this section, right? So recall the group permutation, the group homomorphism that we have seen in section 0, section 1, and section 2. What I mean by isomorphism before, we see that two groups are isomorphism or group isomorphism if it satisfies the homomorphism property and it satisfies the one-to-one and onto mapping from one group to the other one. All right. So now in this section, we're going to look at group homomorphism only. Right. It means that if we have a mapping that is isomorphism, then it's fine. It will also satisfy the homomorphism property. Okay, but in some cases we only the mapping only satisfy homomorphism property but not the one-to-one and onto. So we still can say that this is a group homomorphism. All right. So in overall, we can what we can say is that every group isomorphism is a group homomorphism, but a group homomorphism may not be a group isomorphism. Okay, because we still need to check for the one-to-one and onto property. Okay, so anyway, we define again what is a group homomorphism. So we need a mapping from group G to G prime. Okay, and then the map is homomorphism if it satisfies the usual homomorphism property. All right, so recall we have a domain, we have a codomain of the mapping, and then pay attention that the operation on the left side in the parenthesis here is the operation on the domain, and then the operation on the right side of this equation represented by the operation in the codomain G prime. Okay, so this property will hold for all AB taken from the group G. So AB taken from the domain, right? So we say that phi of AB equal to phi of A multiply phi of B. Okay, so phi of A means the mapping of A, phi of B means the mapping of B, and then phi of AB means the mapping of A multiply B in the domain. Okay, so multiply first and then sign it into the function phi, right? So this was homomorphism property. We have seen this before, but maybe we have not talked much about it. Okay, this time we will talk more about this homomorphism property. right? Let's look at an example. Okay, look at an example of a homomorphism. So consider a mapping from real number, group of real number, into group of circle. Okay, so recall that, and then also by now you should already be keen or comfortable with the list of groups that we have had so far. So when we say about real number group, we actually need to already know that this is an additive group. Additive group means the binary operation is addition, okay, and then the identity is 0, okay, and then inverse for each element is the negative of that element, okay. So that should be at the end of your fingertips already by now. All right, and then the codomain here is a circle group. Okay, we found this in section 3. So recall that this circle group contains the complex number with magnitude 1, whereby if you plot it on the real imaginary plane, you will form a circle, sorry. Okay, so that's why we call it as a circle group. Okay, so anyway, this is a complex number with with magnitude 1. This is a group of real number, of course under addition, and then in the codomain the operation is multiplication of complex number. Domain operation is addition of real number. All right, so given here that the definition of mapping is phi of x will map to this complex number, right? So because we are already very comfortable with the Euler form, so I may want to skip this form. Okay, if I were you, I will skip this polar form, okay, because we have already familiar or comfortable enough with the Euler form of the complex number. Okay, so we use the Euler form, but if you prefer polar form, you can go back to polar form, right? For me, because we have used Euler form for most I can say all of my examples, so we stick to the Euler form, and then it will be easier in terms of multiplication of complex number, right? So we say that any x will map to e to pi I x, right? So this is from the domain, it's sent to phi, okay, from the x from the domain, sent to phi, and then will map to e to pi I x, right? So now we check for the homomorphism property. So if we have phi of a plus b, so obviously our x is a plus b. So now it becomes e to pi I in multiply with a plus b. Okay, because a plus b is our x now. Alright. So now that is it about it. Again, this one I will again skip. I will again sort of not using the polar form, right? So now we see that on the right side of this, what we had just now, actually it is also equal to e to pi ai multiply e to pi bi. Okay, what happened here is just I expand the exponential there. Okay, I expand the parenthesis of a plus b there, right? So we have that, and then obviously e to pi, sorry, yeah. Okay, so e to pi ai here is our phi of a, and then e to pi bi is our phi of b. So clearly it satisfies it satisfies the homomorphism property. Okay, so we say that the mapping or the phi is a group homomorphism. Okay, so that is the conclusion about homomorphism, right? And then if we move further, a little bit further, we say that phi maps onto U. Okay, it maps onto U because each element on the circle has a pre-image. All right. However, it is not one-to-one. Okay, it is not one-to-one. So recall back in section 3 how it is not one-to-one, right? For example, I can say that ei to pi I dengan ei for pi I will be of the same values. Okay, means that I can say that phi, what I mean is that phi of 1 equal to ei to pi, I, sorry, dah ada I. Okay, EI 2 pi. And then if I take phi of, let's say 2 example, so I say that EI 4 pi. Okay, but EI 2 pi and EI 4 pi are actually the same complex number. Okay, we will see that again in the upcoming example. Okay, so that anyway, that is why we say that it is not isomorphism, because it doesn't satisfy the one-to-one property. Okay, but however, we are checking what the group homomorphism. We see that phi here is a group homomorphism. Fine. All right. The next thing we may want to look at is that where does the identity maps? Okay, we see that identity 0 from the domain nicely maps to 1, the identity in the codomain U. All right. So we see that identity in the domain will map to identity in the codomain. And then next one, for the inverse of each element, we mentioned just now, each element in the domain, the inverse is negative of that element. So if we check for the negative of that element, it will go to E minus 2 pi ix, which is also equal to E 2 pi ix. And then E 2 pi ix is of course inverse for E 2 pi ix. Right? 1 over E 2 pi ix is the inverse for E 2 pi ix, because if you multiply the 2, we get 1. So we say that this is also the inverse for phi x. Okay, phi x just now. Okay, so that is the extension of this example. Okay, why we talk about this identity and inverse? Because we want to come up with a proper, with a nice property at the end of this video. Right? Okay, before we go to that one, look at another example. Okay, so recall our nth root of unity, un. Okay, so all of you should already be keen about what are the complex number in here, right? So we're talking about all the complex number that is when we raise it to the power of n equal to 1, and we have seen before nth root of unity will have n number of elements. Okay, for example, U28 will have 28 complex number, and then all of them are separated by 2 pi over 28, and then U4 will be another set of 4 complex number with radius with magnitude 1, where the angle of each of them is separated by a pi or 2 pi over 4, right? Okay, anyway, that's about it, about who they are. And then given that the mapping is this, phi of z will map to z to the power of 7. What is z? Z is the element taken from U28, right, from the domain. A complex number. So to check whether it is well defined, we may want to check whether it is well defined first. So we can see that if we take any complex number from U28, it is when you raise it to the power 28 will be equal to 1. Okay, that is the definition of the nth root of unity. And then therefore, U28 you can also state it as in z power of 7 to the power of 4. Okay, which is also equal to 1. Okay, so this implies that integer mode z to the power of 7 is in fourth root of unity. Alright, so z power of 7 is in fourth root of unity. So now we check for the homomorphism property. Okay, so we see that z1, z2, let's say z1, z2 taken from the domain U28, and then it will be equal to z1, z2 to the power of 7, and then use the usual property of power 7. It will be equal to z1 power 7, z2 power 7, but z1 is a mapping of z1 under phi, and then z2 power 7 is a mapping of z2 under phi as well. Okay, so as previous example, we say that this phi here is a group homomorphism. Okay, homomorphism. Again, and you can see that it is not isomorphism because, of course, it has no one-to-one and onto mapping. Okay, U28 has 28 elements, U4 has only 4 elements. Of course, you can not have one-to-one and onto mapping. Okay, anyway, it satisfies the homomorphism property, which is good, right? And then, like the previous example, we want to see where the identity maps. See, you can see that identity in U28 is 1. So if you bring it in, you put it into the mapping phi of 1 equal to 1 power 7, again equal to 1. So we see that identity in U28 will map the identity 1 also in U4. Okay, that's about identity. So it is congruent to the previous example where the identity 0 maps to identity 1 in the codomain. This one, domain identity 1 maps to identity 1 in the codomain as well. Alright? So, and then furthermore, when we talk about the inverse, the same thing happens. When we take the inverse of Z from the domain U28, of course it is inverse of Z, which is Z power of minus 7. So Z power of minus 7 also equal to Z power of 7 power of minus 1, which is inverse for Z power of 7. Okay, so inverse for Z power of 7, if you put, if you look at the mapping, it also means the mapping of Z. So this is the inverse of phi of Z. Right, so the inverse of that mapping of Z, right? So of course you can see that the inverse also preserved like that. Okay, so now we define some notation, okay, before we go into the important property in this video. Okay, so we say that let phi is a mapping from X into Y. Okay, so X into Y, here X and Y can be grouped, can be set, okay, because we want to generalize this definition. Alright, suppose that A is a subset of X, B is a subset of Y. Okay, this is a symbol subset. Okay, I'll recall that this is a symbol subset. So phi of A here. Okay, so look at that. Okay, so phi of A. So we use a sorry. Okay, so we use the square bracket here. Okay, square bracket here. To say that it is a set. Okay, it is a set. Phi of the whole set A means that we talk about phi of A for every A in the set A. Okay, so means that it will form a set. Okay, apakah set itu? What is the set? The set where we take all the element of the set A, the subset A, and then send it into the mapping phi. Okay, so this subset, okay, this subset is what we call the image of A in Y under mapping phi. Definition panjang sedikit. So this is the image of the subset A. Okay, image of subset A in where? In the codomain. Alright. Likewise, if we take the inverse mapping of B, B is a subset in the codomain there, and it also will form this subset. Apakah subset itu? Subsetnya ialah A in A such that phi of A is in B, mana pre-image of each element dalam subset B dalam yang ada dalam codomain, we call as the inverse image of B under the mapping phi. Okay, so why we define this? We want to show 4 properties of homomorphism. Okay, all right. So in terms of isomorphism, it's easy. They are because it has one-to-one and onto mapping. We are interested into the homomorphism properties, right? So this is theorem 8.5, an important theorem about homomorphism. Okay, what we can conclude if we have a group homomorphism like what we had in the previous 2 examples. Okay, so we have touched a little bit about the identity and inverse up there. Okay, so after all, we actually have 4 properties altogether. Okay, if we have a group homomorphism, actually we can conclude 4 properties. The first one is that the identity element in the domain G, then phi of E is the identity in the codomain G prime. Okay, this we have seen an example just now, but in this theorem we need to prove it. The proof is not that long; it's quite short. Okay, you need to read this proof. Okay, so you need to know how to read this proof. Okay, if you don't know how to read this proof, please come back to me. Okay, I'm expecting you or all of you are already keen about reading mathematical properties. Okay, after all, you are doing your final year project, you are reading a lot of journals, so you should be able to read this properly and then understand it properly as well. But if you find it hard to understand, always come back and ask me. Okay, and then I reinstate here that if you don't ask, mean that you understand. Okay, and then if you don't understand, you need to ask me. Okay, seek for clarification. Right? Okay, so that's property 1. Property 2 says that if A is in G, we take any element A in the domain, So the mapping of inverse will be the inverse of the mapping of A. Okay, also what we have seen by example up there, and then by proof is given here. Okay, also quite short. Okay, proof for that one. Number 3, if H is a subgroup of G. Okay, so we have a group G and then we have some subgroup in that group G. Then we see that phi of H. Okay, what is phi of H? This one is the image that we seen just in the previous definition just now. That will become a subgroup of G prime. Okay, so this is a very interesting property. Number 3, the proof is here. Okay, this one pernah keluar exam. Okay, so make sure you read this. Okay, also for your group assignment. Okay, not only you need to read this proof, you need to understand the proof. Okay, because for example, during the presentation, I will ask some question. Okay, for example, if you look at property number 3, the proof is here, right? The proof is here. So it take the, as usual, it take the hypothesis first. Okay, the hypothesis says that H is subgroup of G, so you need to use all the properties of subgroup that you know. All right, and then it take phi of A and phi of B be any two elements in the image of phi of H. Okay, sebab apa? Sebab dia tunjukkan this one is a subgroup of G prime, and dia kata then phi A phi B equal to phi of AB, so that we see that phi A phi B is in the image. Okay, so some student they present saja benda ni and then they terus proceed to the next one and then the example. Okay, and then come the question from the examiner, which is me or Madam Norida later. We will ask you, for example, we ask you why you say this. Okay, so you need to know why you say this. Okay, so that's the trick. Okay, the turning point of this proof. Okay, why you say that this is equal to that. Okay, so you need to have an answer to that one. Okay, so please make sure you know the why. Okay, don't just read. You also need to have an ample critical thinking. Means that you query back the proof. Why is this? Why is that? All right. So that's property number 3. Okay. So and then property number 4. Also, if K prime is a group of G prime. Okay, looking on the codomain direction, we say that the inverse image will be a subgroup of G. Alright, so that will be this one here is the proof for that property. Okay, again you need to read it line by line properly and then come back to me if you have inquiry. Alright, about that. Okay, and then of course you need to come up with an example. Okay, so this is an important properties. When we come back, when I see you again in class, please if you have questions, please ask. Alright. So finally, we want to define the kernel. Okay, define the kernel. So we have had this one, G to G prime be a homomorphism, and then E prime the identity of G prime. Now we say that the set containing E prime is a subgroup of G prime, of course, because it is the trivial subgroup. Okay, the trivial subgroup in the codomain. Now the inverse image of E prime is a subgroup of G. This is by statement 4 just now of the previous property, alright, our previous theorem 8.5. So this subgroup is critical to the study of homomorphism. Which subgroup? This subgroup here. Okay, the inverse image here is a critical study of homomorphism. Okay, so we define a kernel now, and then I will continue the topic of kernel or the video on kernel in the next video, right? But before we go to that one, we state here first the definition of kernel. Okay, what is a kernel? The kernel is what we mentioned here lah, the inverse image. Okay, so we state it properly here by definition. Like say that we have the homomorphism from G to G prime, this subgroup just now that we mentioned. What are the elements? The elements are all the elements in G such that phi of X will map to E prime, the inverse, the identity in the codomain. Alright, is the kernel of phi denoted by this notation. Okay, so that's the kernel. Alright. Okay. Okay. So that's the definition of kernel. If you want to have a quick a quick example of kernel. We will have we will see the example in the next video, but if you want to query a little bit by now, we have seen